Do these papers finally explain how LLMs work? Today we're going to be looking at Bayesian reasoning, LLMs, and knowledge creation. Yes, something I've talked about a lot over the last few years. However, a trilogy of research papers has recently been published that claims to explain how, precisely, LLMs like Grok, ChatGPT, Claude, and so on achieve their amazing proficiency. For some time now, there has been limited to no good explanations at the emergent level of how the transformer architecture works. Yes, we can wave our hands and refer to neurons and attention, passes and self-attention and so on, but that does not really explain how these things work in a way that the average person would now be able to say, now I get it. I'll come back to this. In any case, my purpose here is to assess claims made by the authors in these three papers, in particular by Vishal Misra, who claims to be able to explain what is happening inside what was hitherto the black box that is the transformer. I read the papers on this, thanks to Naval for the tip, and then listened to an interview with Vishal himself, which was extremely informative, and we'll come back to that as well. I was excited in particular to hear Vishal talk in the interview about how these LLMs cannot possibly just recursively improve without limit, precisely because they can never get outside their training data. This is something I've been harping on about as an amateur commentator on these things for years now, and yet finally I'm hearing it from a professional who works in the area. He's a computer scientist, he's a university academic. Let me just emphasize that for those who are only persuaded by appeals to authority, and there are many, I've even debated some. Vishal is a Vice Dean of Computing and AI at Columbia University, in addition to being a real innovator, especially in the early internet. But relevant to us here now, he's an expert in LLMs, and he's been working with them and experimenting with them since GPT-3, not just as a casual user like most of us, but as a scientist. So this episode is going to be about his and his colleagues' work because I agree with it, which is kind of rare. It's a departure for me because more often than not, when I'm talking about AI and what other people are saying about AI and AGI and so on, people will know if you're a listener to this channel that I disagree more often than not with the experts who claim to know how LLMs work or what they are and what they're becoming and all that kind of thing. So this is refreshing for me. But first, I am going to take some very broad tangents to talk about things, well, I'm just interested in, which is relevant to all of this. If you're very, very familiar with my channel and me and what I say about this stuff, or if you're a long-time listener to Talkcast, well, you might want to skip to other parts of this episode. Happily, AI organizes these long episodes into chapters, at least on YouTube, so you can find where I begin talking about something like the papers in particular and Vishal's comments if you prefer. So first, to some background. When large language models, LLMs, appeared, and appeared quite abruptly in the eyes of many, beginning with GPT, GPT stands for Generative Pre-trained Transformer, especially GPT-3, then OpenAI's ChatGPT, it was unclear exactly how they achieved the amazing feats they did. It was known, of course, they were based upon the so-called transformer architecture, a special kind of software which arose from the Attention is All You Need research paper. You can see that here. That was the research that led to the algorithm, that led to code, and eventually then apps like ChatGPT and all those many AI assistants out there amongst much other advances in AI, all of those movie-making apps and so on. This was an astonishing leap in progress no one predicted, nor could have predicted, precisely because it was a breakthrough. That's the nature of breakthroughs. They're not extrapolations from past discoveries. It's not like there were pretty bad chatbots, then pretty good chatbots, then really good chatbots and excellent chatbots that passed the Turing test and all that sort of stuff. No, it was terrible chatbots and then very, very good ones, which seem to only get better and get better extremely rapidly. Although they seem to have plateaued recently. They've almost reached a local maxima of some kind. At least this rapid improvement in the facility of chatbots is the experience of users and the public, if not the insiders and the experts and the engineers who might have been privy to early iterations of the transformer architecture. In any case, what happened with chatbots and generative AI more broadly paralleled what sometimes happens in groundbreaking science. Einstein's creation of the theory of general relativity was surprising and unexpected by the physics community. Darwin's creation of evolution by natural selection, a giant leap in the community of biologists and for the world's understanding of what life is, or at least what the diversity of species are and how they arose. These discoveries and theoretical inventions, this knowledge creation, arrived on the scene in a surprising and rapid way. But the other surprising thing about ChatGPT and its relatives and descendants has not been just how quickly it seemed to appear from nowhere or how good it was, but also, and this is key, no one could explain, as I've already said, at a high level, at the emergent level, how these systems are able to accomplish the task of constructing text, in particular text, so well. What was going on inside the black box called the transformer? Of course, people can say things like next token prediction, I was saying that, and talk about recurrent neural networks and the hidden layers, training, weights, vectors, passes, and so on and so forth. But again, that's all at what might be called the reductive level. It would be as if to explain the events of World War II in terms of the motion of atoms following the laws of physics. Technically correct in an almost vacuous sense, but not an explanation at the right level, which would consist not of terms like atom and law of motion, but rather Germany and Hitler and conflict and Poland and tanks, and you get the picture. So what is the equivalent higher level explanation for how LLMs achieve their excellent capabilities? Many have suggested various ways of coming at this. These papers, however, by Agarwal, Dalal, and Misra, may shed some new light on how LLMs reason, and in doing so, rule out the possibility that there is any pathway from present LLM architecture to AGI, ruling it out for reasons different to the ones that I would normally use. Now, I should say at this time that one of the authors in particular, Vishal Misra, has spoken at some length about AGI, even if this term AGI is not mentioned in any of these papers recently published, of which he's one of the authors. But what does he say more broadly about AGI? Well, what he says, I think, is right on the money as far as I can tell most of the time. I don't know if he's Popperian, I don't know if he's read David Deutsch, but he seems to get the black and white distinction between these chatbots and actual people, or AGI. And that is something other experts and thought leaders in the field so often seem not to. They seem terribly confused. Again, you may have seen me in debates with some people who are terribly confused on that point. It remains a minority opinion among commentators that continued improvements in Grok, ChatGPT, Claude, Gemini, and so on cannot possibly lead to artificial general intelligence, a true universal explainer, or an artificial person, in other words. Both Elon Musk of Grok and Sam Altman, OpenAI, ChatGPT, are emblematic of, and in a sense they're the thought leaders of, this majority opinion among tech enthusiasts, commentators, and even engineers and other professionals working in the field. They think more computers, they say, will lead to AGI and then ASI. As I often say, that's been said by Bostrom and even before in the early 2000s. Some useful concepts before we continue. And again, if you're a listener to Topcast, you will be very familiar with some of this material, but I think it's worthwhile going over again. Firstly, epistemological induction. What is it? Well, this is the misconception that from some amount of data, an explanation can be derived. The classic idea is that from observing some number of white swans, the conclusion, all swans are white, can be derived with some degree of certainty. This is a logical fallacy. It's the fallacy of hasty generalization, because no finite amount of data collection can possibly allow one to conclude all swans are white, because we can never rule out the existence, somewhere in the universe, as yet unobserved, where there lurks a non-white swan. But induction is even worse than that, in fact, because its defenders, the defenders of induction, inductivists, are not only saying we can extrapolate from data to predictions by drawing straight lines through points on a graph, that kind of thing. No, they're trying to argue that entire scientific theories or explanations are generated in this way. Namely, by observing a finite number of instances, we can derive a grand explanation of some physical phenomena. So never mind all swans are white, which isn't even an explanation. Something like the Big Bang Theory was simply derived or induced by looking at data and extrapolating. That would be induction if it worked. In other words, the data would not just give you what happens, the prediction, but it would also tell you why it happens. In truth, we know what happened historically with the Big Bang Theory, and this is true for all scientific theories. Problems were encountered with existing explanations, and solutions, in other words, new explanations, were conjectured, which were tested against the evidence. In the case of the Big Bang, Einstein's theory of general relativity predicted a dynamic universe that should have been expanding. That's a problem for the existing conception of the universe, the Newtonian one. Well, evidence in the form of the red shift of galaxies. That was a problem at first. And later, the heat left over from the Big Bang, the cosmic microwave background, and even the ratio of hydrogen to helium in the universe explained why the Big Bang was necessary to solve all of those problems. That was the evidence, and the Big Bang explanation explained why the evidence was the way it was. The theory explained the evidence. And that evidence ruled out a static universe. George Lemaitre had been the first to guess that the universe began as a primeval atom, so he called it. And then this explained the data that was seen by that Big Bang theory that he came up with. He didn't call it that. That was Fred Hoyle who called it the Big Bang. But George Lemaitre's Big Bang theory explained why the data was the way it was. In particular, why the galaxies were redshifted as they were. Okay, so there's a refutation of induction. Okay, this use of data to just get to an explanation in some way. Now, despite that refutation of induction I've just given you there, which is a version of, or derived, I suppose, from the explanation that Karl Popper first gave, induction has nonetheless persisted in the minds of scientists and philosophers and other people. It's persisted zombie-like as a meme running on the minds of many intellectuals. And they pass it on from generation to generation, student after student. And so people now still learn that while mathematics and logic rely upon deductive reasoning, a lower certainty form of reasoning known as inductive reasoning operates in the sciences. Precisely how many swans one must observe to conclude all swans are white is a mystery. Induction does not say and cannot say. Nonetheless, its defenders, they just ignore that fatal logical flaw in the argument. This problem of induction, Popper explained, was no problem, is no problem at all, precisely because science is, in truth, a problem-solving exercise, where explanations are created, literally created in the minds of scientists, and then tested against reality by experiments which decide between theories or rule out their rivals, if you like. How scientists create explanations in their minds remains a mystery. As happens in academia, philosophers coined the term abduction to label the process of knowledge creation. But that's no solution. It's just a label for the same process. You're guessing or conjecturing. Simply calling conjecture formation or explanation creation a new term like abduction does not tell us what abduction or explanation creation actually is or how it works. If we knew that, we'd have an understanding of the mental process, more precisely the code or the algorithm that can generate truly novel and good explanations of reality. Over the decades since, despite this devastating refutation by Popper, committed inductivists have been deaf to such criticisms, either through ignorance or misunderstanding. And so a newer, more mathematically sophisticated, but essentially the same line of argument was born: Bayesian epistemology. Bayesian epistemology purports to explain how knowledge is generated. Epistemology as a subject is the domain of inquiry concerned with what knowledge is and how it grows. Bayes' theorem is as good a mathematical theorem as any other, like Pythagoras' theorem. Bayes' theorem deals in known probabilities. A known probability, sometimes referred to as the prior probability, or just the prior, is given by facts about the system under consideration. So, for example, if we consider a perfect, ideal, abstract die, we know it has 6 sides, and each side has a 1 in 6 chance of coming up, if rolled fairly. The 6 in the denominator logically falls out of the fact that the die has 6 sides, and nothing magical or quantum or anything else affects its perfect fairness. Again, here we are considering imaginary, abstract dice, not real dice, which are indeed subject to quantum laws of physics, and so, in reality, do not obey the probability calculus exactly. I have spent some time already explaining Bayes' theorem right here, at length. And so I'm not going to recapitulate all the arguments and, in particular, the mathematics or arithmetic and calculations that appear there. From Bayes' theorem, philosophers and others move to what is sometimes a more nebulous term, Bayesian reasoning. So, as the classical example goes, let's make up a name, if Wayne from Wisconsin in the winter walks into the doctor's office complaining of fever and lethargy and says he's Googled his symptoms and he thinks he has malaria, the doctor may well at first think of completely discounting Dr. Google and ask further questions of Wayne rather than sending him off for a blood test to check for malaria straight away. One might loosely say the doctor assigns a low probability of Wayne having the malaria, given Wisconsin in winter is freezing cold and mosquitoes are rare there at any time, much less malaria-carrying ones. However, if the doctor's first question to Wayne is, "Where have you been recently, Wayne?" and then Wayne answers, "Well, I just got back from spending 3 months in the Amazon, touring Brazil and Paraguay and Bolivia, and there were lots of mosquitoes there," then the doctor updates his prior and sends Wayne for the blood test he needs in order to rule out other possible causes. A positive blood test would leave malaria as the most reasonable conclusion. In the article I wrote, which you can check out, I suppose, on Bayesianism, I used some reasonable numbers to actually calculate what the probabilities would be in the scenario if you wanted to figure out how Bayes' theorem actually works mathematically speaking, if you're inclined to go through the arithmetic. But absent those numbers, okay, pretending you're not actually using Bayes' theorem exactly, you're just reasoning, others sometimes call what I've just gone through there Bayesian reasoning, even if, again, Bayes' theorem is never explicitly or even actually used. Doctors don't actually tend to pull out pocket calculators in their consultation rooms when they're trying to figure out what you have. So are they doing Bayesian reasoning? Now, people call it that, don't they? And one can call it Bayesian if one likes. The terminology doesn't matter. But do notice that in general, when a doctor does that sort of thing, they aren't using Bayes' theorem. They might not even know what Bayes' theorem even is, much less be able to use it to calculate a probability. And in fact, they probably can't use it to calculate the probability anyway because the probabilities just aren't known for this sort of thing. But when you're in mathematics class, they invent some numbers, let's say, or make some reasonable estimates. However, whatever the case, because of this kind of reasoning, where we seem to have a problem with no solution yet known, and then evidence is introduced to pare down the spectrum of possible causes to a probable cause, some scientists and others have argued that Bayesian epistemology is how science works. Of course, I'm using the Bayesian framework there and explaining that. What I would normally say is you're not paring it down to a probable cause, you're paring it down to the best explanation, and usually the only good explanation available to you. When there are many theories on offer, so the proponents of Bayesian epistemology argue, we gather evidence, and the evidence allows us to calculate the probability of each theory being true. What this misses, of course, is that in the artificial Dr. and Wayne with malaria scenario I've just given you, the whole example is constructed for the purpose of illustrating how Bayes' theorem can work when we do have a single solution, an explanation, a good explanation, already known as a distinct possibility. It's literally begging the question as to whether or not this is how scientific explanations are generated and then compared one against another. Malaria is already well known about. It's a well-known disease with well-known symptoms. It has to be, for the example to work. But no amount of applying Bayes' theorem in the way I've just described in that example will ever generate a cause for a disease not already known about. In other words, if the blood test comes back negative for malaria, all of that increased confidence in the prior probability for malaria is wiped out by a single observation of a negative blood test. And worse, Bayes' theorem can never point to any other cause, because none has yet been conjectured. If Wayne's symptoms are caused by a virus no one in the history of humanity has ever encountered before, Bayesian epistemology is impotent in explaining how such a solution might ever arise. Karl Popper, on the other hand, explains that such a solution must be creatively sought first, and not derived. Scientists must conjecture explanations. How? Well, after Wayne's blood is tested, then something like tropical disease scientists must go to the Amazon in search of new viruses, if this is indeed where he got sick, and there was sufficient interest in finding out why. They, the scientists, would have a problem. Now, imagination and experiment by scientists would occur. And the truth is, when they succeed, when they succeed, almost always they find the solution, the one and only solution. Not two solutions, not many solutions, much less 10 solutions, which they have to use Bayes' theorem on in order to figure out which is the most likely. And when they find the solution, they don't tend to say, well, we found the solution with 90% confidence. At least they shouldn't, and it's meaningless if they do. They just say, we found the virus, we've detected it, and this is the cause of the disease. Hence, Bayes' theorem in epistemology is of no use whatsoever for explanation creation, or even of deciding between explanations. The central task of a scientist is the explanation creation, and Bayesian epistemology is completely silent on all of that. Bayes' theorem is of no use prior to the scientists creating the explanation, it has no use there. And in fact, it has no use after the explanation is created either, because if there is a rival, in the rare case that there is a rival, an experiment is done to decide between the two explanations guessed. Just as an aside here, one of my favourite television series to watch ever, and it's all available on YouTube, is Air Crash Investigations. Every single one of those episodes is a refined example of critical rationalism. They don't use Bayesianism. Sure, sometimes the language they use is incorrect. They may speak in terms of beliefs and probabilities. But what's actually going on in that show, when you pay attention, is conjecture and refutation, down to a T, until they settle on the one and only explanation. Often, the explanation is, so we might say, overdetermined, many causes pointing to the one explanation, the one good explanation. Anyway, the point is they do not end up in a situation ever where they're weighing theories one against the other or using theorems to assess the probability or likelihood of each. No. When it's life and death and something as critical as airline passenger safety, the investigators know that they have to guess at the answers and then rule them out one by one methodically until they arrive at one they simply cannot rule out because it explains everything. More often than not, they then go about trying to recreate the accident as well in simulators or whatever else as an extra check. They are left then, again, with the very, very good explanation. Not a probable explanation or a likely cause, the explanation, the only explanation known, with all others discarded as simply not possible. I think I've seen a few rare episodes where they don't actually ever find out what the answer is, but they put fixes in place that prevent the problem from actually occurring. One I was watching recently was the rudder on the tail of a 747 got locked in place to the hard left or something, causing aeroplanes to turn. And this is a known fault within the aeroplane. Now, they can put a fix in place to prevent the rudder from doing that, but in the episode I saw, they still weren't sure exactly what caused the rudder to malfunction. That's one of the rare cases where I was saying where they didn't actually find out the answer. Anyway, we might well ask then, what place is there for so-called Bayesian reasoning? And what does any of this discussion have to do with LLMs? Science is about solving scientific problems. It's about constructing explanations of what was hitherto unknown. In other words, the solutions in science are unknown to everyone initially. So actual creativity must be deployed to generate the solutions. They cannot possibly, for the reasons I've previously given, be derived from existing information. They must be invented. Scientific theories must be invented, created, generated. Put it how you will. Science deals with the unknown and then makes it known. More broadly, human cognition does this all the time. We search for answers in our minds to the questions we have. For the answers come from within us. We do not find them out there. What we find out there are clues, evidence, data. But none of those are explanations. We want explanations of those things, explanations of the clues, of the evidence, of the data. The clues, evidence, and data have to be interpreted and used as critiques of the answers we guess. Humans are constantly dealing with the unknown because the world is, in very large part, both unknown and unpredictable. One may think that because physical reality is governed by deterministic physical laws, and it is, that it must follow, therefore, that the future is predictable or knowable by humans. But in general, it's not. Here's the video I once made outlining the 3 ways in which there are very strong prohibitions on us knowing the future from the perspective of physics. Now, that's science, and science deals with the real physical world and real problems which have no known solutions. But what if we move the discussion out of the real physical world and into a curated digital library of data? What then? Well, now the rules can change. If we're talking about a library of information, we can begin to use abstract mathematics rather than the method of scientific inquiry to analyse and even extrapolate from parts of the data to conclusions that come from the data. What I am talking about now is the training data and the libraries of information utilised by LLMs. LLMs are in general trained on vast quantities of data. Sometimes the data is specialised. For example, Sam Harris, the podcaster, has said he has trained an LLM on all the text he's ever written and all the words he's ever said over 2 decades of public outreach, or at least someone did that for him. Many, many millions of words that Sam Harris has ever uttered mean that an LLM can be produced which can get Sam Harris-like responses to literally any question. Many people are using specialised, more narrow LLMs for many kinds of purposes. However, most people are more familiar with the general LLMs like Grok and ChatGPT and so on. Those are trained on as much information as their owners can get a hold of. All the libraries of the world, all the YouTube videos, all the text on the internet, all publicly available encyclopedias, every newspaper article or interview that they can find, all the scientific databases and so on for almost every piece of information that appears as some sort of text anywhere ever. Well, almost anyway. Whatever the case, these LLMs are trained on and draw upon a reservoir of data unlike anything humanity has ever seen before in many cases. Given so much data, it is little wonder it can be recombined in ways never before seen in the history of humanity. This novelty can, and continues to, give the illusion of creativity. What's the difference? The difference is that a person is genuinely creative, as I have said ad nauseum. From scant evidence out there in the real world, people conjecture grand explanations. They don't derive it, they conjecture. Einstein saw light and then in his mind contemplated how that light might behave, and he constructed theories of relativity. Charles Darwin saw beaks of finches and some tortoises, and from limited observations, again, within his own mind, constructed a grand theory of evolution by natural selection. He did not derive the theory from the finches or the tortoises. He saw a problem. Why were all those species so different, but some so similar? And then he thought of a solution, and then he observed more in an attempt to rule out his own theory. That's the process of genuine creativity. The theory of evolution by natural selection was nowhere at first. It simply did not exist. It was not out there resting on a rock on the Galapagos Islands, nor carried on the back of a tortoise, nor delivered to Darwin from the beak of a finch. It came from his mind, not extrapolated, created. On the other hand, if I shuffle a deck of cards, then in all likelihood, I will produce a sequence of 52 cards that is novel. By novel, we mean new, or never before seen in the history of the world. But I would not say I have created this sequence. Once I have the 52 cards, then all possible sequences follow as a matter of logic. Now, this is because the number of possible combinations for 52 cards is factorial 52, okay, typically written as 52 exclamation mark. And that means 52 times 51 times 50 times 49, so on, so on, so on, all the way down to times 2 times 1, which is a number that is 8 followed by approximately 67 zeros. In other words, every random shuffling of a deck of 52 cards is highly likely to be unique in the history of the universe because that number is just that big. So novelty here means something like never seen before. Decks of cards can produce novelty. So can people, and so can LLMs. But unlike decks of cards, where random shuffling produces novelty, an LLM takes the data, the equivalent of the cards, and organizes them into sensible strings. But how? How can it consistently get right, and this is the kind of example that's used a lot, that the next word in the sentence, the cat sat on the, will be Matt? How could it guess Matt, and reliably so, and then repeat for many other sentences and more complex cases? I'll come back to that, and one of the authors of the paper will speak about that as well. I need to emphasize, people are not just predicting the next word or sentence, like an LM, to get novelty at times. What people do uniquely is create. They don't just generate novelty. They don't just shuffle or reorganize and extrapolate. They bring something into the world that wasn't there before. A random sequence of cards is there in the world. It's in the cards in a sense, at least abstractly speaking. All possible combinations, in theory, could be written down using a computer given enough time and memory. In a similar way, all information and all explanatory knowledge already known can appear in a library or database somewhere and then reorganized to give novelty. Of course, if it were shuffled, it would give nonsense. There would be novelty, it would be nonsense. The genius of the LLM is that the reorganization is in general not a shuffling. It is a sensible reordering. How does that work? Again, at the level of the transformer architecture, the low-level reductive explanation is next token prediction. This means that a statistical model of language is made where in, for example, the English language, certain letters appear more frequently after others. It's highly likely that any Q is going to be followed by a U, although not 100% of the time, as anyone who has flown the airline Qantas can attest. But the probability of U's following Q's is high, maybe 99.9% of the time. Now repeat for all other letters. Now do a similar thing for words. Perhaps if we began on July, and then the computer needed to predict the next word, many options would arise, but the word the would be most probable perhaps. On July the, and then perhaps fourth would be more common than any other possible word. In reality, the transformer architecture does pass it back and forth over the data as a way of checking and rechecking if the words and sentences and paragraphs fit the pattern of similar passages of text that appeared in its already existing library and training data. Now, that's kind of at a low level, and it's a bit crude and hand-wavy, as we like to say. But how can the transformer produce novel answers and seemingly reason to such excellent responses? Well, as I say, answers to that have been posed in 3 recent papers titled by the authors the Bayesian attention trilogy. They claim that Bayesian reasoning is kind of invented by the transformer and utilized by the transformer architecture in order to be able to reason its way to quality responses. Is that possible, though? Haven't I been saying Bayesian reasoning isn't really a thing? No, well, it's very, very possible. It's eminently possible precisely for the same reasons that Bayesian reasoning or probabilistic reasoning is useful in closed systems, such as gambling and cards, for example. We have a finite list of cards, and there are only so many ways that they can be shuffled, even if the number is monstrously large, as we've already seen. If we take one card from the deck and say it's the ace of spades, we can reason that the next card drawn could be any of the remaining 51 cards with an equal probability of being drawn. If you're a gambler, betting on the next card isn't a good bet because the odds are so low. If someone gifts you $1,000 for the sole purpose of doubling your money, if you can pick the next card accurately out of the 51 cards remaining, you're likely to lose. It's very hard to pick a random card out of 51 cards. Although you can rule out that it's going to be the ace of spades, it's already been drawn. But if this process of picking cards from the deck randomly gets you down to only 2 cards remaining and you've kept track of all the cards so far drawn, then you have a pretty good chance of doubling your money if you can pick the next card because it's going to be 50-50. That you'll get it right. It's a reasonable bet if it's not your money. Probability is like that. With ever more information about some closed system, as I'm going to call it, we can narrow down the odds. One can call that Bayesian reasoning in a pretty loose sense, but if one is actually plugging in the numbers as they go, updating their prior probability that the final card to be drawn is, say, the Queen of Hearts, that probability that it is the Queen of Hearts rises and rises until such a time it is drawn before the final card is drawn, in which case the probability becomes 0. Again, if you are actually gambling, if it's not your money, because the rational thing to do is, of course, not bet, and you're placing bets, the decision theoretic or most reasonable tack to take is to bet a small amount. The Queen of Hearts will be the next card drawn, but increase the amount you're going to bet each time the Queen is not drawn. So I think it's important that we distinguish when we're using these probabilistic arguments and talking about potential futures or predictions, whatever. It's important that we can define 2 kinds of systems. One we can define as a closed idealized system, as I'm going to call it. And that's one where the denominator of the probability can be known, a priori known, by definition, given the probability calculus. For example, a perfectly abstract die of 6 faces logically requires that each of the 6 faces has an equal 1 in 6 chance of being rolled, if and only if the roll is fair. So, knowing that it's got 6 sides, we know that the denominator in any probability being done is 6. But on the other hand, we can define something that I want to call an open real system as one where the denominator of the probability cannot be known because it cannot be given a priori. There is no definitional way in which to understand these kind of systems, the real life systems. And it cannot be understood a posteriori either, which means after the fact, because the real physical world is governed not by the probability calculus anyway, but rather by the laws of physics, which happen to permit creativity, which brings into reality literal unpredictability because of, in particular, the growth of explanatory knowledge. So, for example, the probability of an asteroid, any asteroid, impacting the surface of the Earth within the next 100 years, let's say for asteroid radii of over 10 meters, the probability of such an asteroid impacting the Earth over the next 100 years cannot be given, even putting aside the fact we cannot exhaustively search, using our present technology, space around the Earth for all unknown asteroids. We don't even know where to look, given we know some large portion come from outside the solar system, possibly even outside the galaxy. But more importantly than that, more importantly than the fact that we can't assign a probability to asteroid impacts because we can't look for them and do a count, is that any asteroid actually detected cannot be given a probability of impact with Earth precisely because its trajectory can be affected by the knowledge created by people who choose, for example, to look for such asteroids and then, using technology, alter their trajectories so that they don't actually impact the Earth. If asteroids are caused to deviate from their trajectories, never hitting the Earth, then the probability of their hitting the Earth is 0. In closed, idealized systems, like abstract dice, the probability calculus can be used to make predictions. This includes predictions that make use of Bayes' theorem. A closed system is isolated from the real world in any number of ways. or can be assumed to be approximately isolated. A real dice, for example, a real physical dice that you roll, is assumed to be approximately an isolated system, and so the probability calculus can be assumed to give approximate rather than exact predictions for how it will land or how the distribution of faces rolled will be over time. In reality, of course, and you can just do the experiment yourself if you don't believe me, if a real dice is rolled 6,000 times, we can actually predict that the number 2 will not be rolled 1,000 times, only approximately so. And if we found the numbers 1 through 6 were indeed, when you did this rolling of the dice 6,000 times, if each of them were rolled exactly 1,000 times, that would be a problem. Because we know, even intuitively, that the actual laws of physics govern dice, not the probability calculus, which would require that each side is rolled 1,000 out of 6,000 times. A closed, isolated system, I will argue, is something like an LLM, and its library and its training data. So the library, the training library of an LLM, the LLM itself, if you like, it's a closed, isolated system. It's disconnected from the real world. All that data is just sitting there, and so therefore, the probability calculus can be used on it. Hence, Bayesian reasoning can be used by the system to predict the next letter, word, sentence, and paragraph, respectively, in any given response provided to a user. It's isolated from the real world, as I say, in a very real sense. It has access only to language and data from its libraries. The real world that the physical sciences study, on the other hand, and even the social sciences, perhaps even more tellingly, are open. They're not closed. They are open not merely to the vast complexity of a universe governed by quantum and other laws, but also to the choices people make. And the choices people make are inherently unpredictable before they are made, precisely because they depend exquisitely on the knowledge people create, literally create. And those cannot possibly be included in the denominator of any fraction used in the probability calculus. What is the probability, for example, that in the next 3,000 years, the history textbooks will contain within them stories of a global population decline over the last millennia? There's no probability of that now. There is no equivalent of a die being rolled. There are no 6 possibilities. There are infinite possibilities, and only some can be guessed at now by the fallible imaginations of people. And it would be wild guessing about whether or not over the next 1,000 years the population of humans on planet Earth is going to decline. What happens over the next millennia is more unpredictable than what happened in the last millennia. And the last millennia could not possibly have been predicted by those in approximately the year 1000. The authors of this trilogy of papers, that I will get to, I promise I'm coming to it, they write in one of the papers, quote, Bayesian inference isn't something transformers do in special cases. It's the native language of attention. It's what these models are, end quote. This, to me, is kind of unsurprising, and it should be unsurprising to you as well, given what the transformer architecture consists of. Vectors represent aspects of language, and the aspects of language are assigned weights. Because the weights are expressed as decimals between 0 and 1, they can be considered probabilities. Hence, the transformer, when doing next token prediction, is literally calculating probabilities, obeying the laws of the probability calculus, or at least that's what it's calculating, that's what it's doing. A theorem of the probability calculus is Bayes' theorem, and so, again, it should be unsurprising that one way of describing what it is doing is Bayesian reasoning, in a literal, mechanistic sense, in a way that really only a mechanical computer could do efficiently. It is sometimes said by some philosophers, Nick Bostrom is of course a name that comes to my mind, they like to say that people are Bayesian reasoners, and that in order to become more rational, which is what we're all aiming for, aren't we? To become more rational, we should all aim to be better Bayesians. But what philosophers like Bostrom cannot possibly mean by being a Bayesian reasoner is literally a Bayesian reasoner in the sense that a computer can be programmed to be. And that is because the human mind is simply not calculating probabilities explicitly. We can wave our hands, of course, and say something like, when you are about to walk out your door of a morning and you grab your umbrella and think, oh, this umbrella's a nuisance, And so to be a better Bayesian, you first look at the sky to check for rain clouds. You'll update your priors if you see no clouds and think, well, okay then, I'll leave the umbrella behind, I won't bother carrying it. But if you're a better Bayesian still, then you go online onto your favourite weather app and check the rain radar for your area. If you see a deep red cloud front moving towards you, well, a better Bayesian would pick up the umbrella again. Now, as I say, that's all hand-waving. The truth is, you are not updating your priors at all. Recall, prior means prior probability. But you don't know the actual probability of it raining. You, like every person, just thinks, I think I'll need the umbrella today, or not. You don't actually say, I've calculated a 30% chance of rain. You certainly do not calculate that number, not in the way an LLM does by first assigning probabilities for whatever reason, and then truly updating the probability using Bayes' theorem and actual calculations to get to a new number when constructing responses to prompts. You, a human being, a person, do not become a better Bayesian by updating your priors. What you can do instead is be a rational person by creatively conjecturing explanations that seem good explanations to you. And when evidence comes in, like the absence or presence of clouds on the radar map or the weather map, you alter your good to you explanation. That's what's going on. And that has to be what goes on because you cannot know the probability. And one reason you cannot know the probability of rain is that there is no probability of rain. The world does not obey the probability calculus. And when I say there is no probability of rain, again, I don't mean the probability of rain is zero. I mean there is no probability of the rain happening or not. There's no probability of anything happening in the real world. The real world is not probabilistic. I'm not trying to be too clever by half when I say it either rains or it doesn't. You either need your umbrella or you won't. Things do not probably happen in the real world. They either do happen or they don't happen. And you can make a prediction about what will happen, not given the probabilities, which again, literally do not exist in the physical world, but rather given an explanation. And note that because of that qualifier, to you, it's good to you, we have an explicit note on all of this. It's you making this explanation. It seems good to you, and you are fallible. So it might well be wrong. Some people are better at predicting things like the weather than others. Typically, those people are called meteorologists. And these days, they can run many reasonably high-fidelity simulations of what might happen in the future, given the conditions now. They can subtly change the conditions moments from now and calculate 100 or more different scenarios. This is something you cannot obviously do in your mind, but their computers can. And having done so, they might find that in 75 out of 100 such simulations they run, they find it is going to rain on you. They can report this as 75% chance of rain. Again, either it rains or it does not. So the 75% chance of rain is telling you not about physical reality, but the methodology and limitations of the processes used by the meteorologists. In other words, it's telling you about the computer simulations. And in that case, the rational person would decide to carry an umbrella if their personal rule is any amount of rain requires an umbrella. In any case, in reality, it will rain any amount or it won't rain any amount. The real world is an open system where things happen or they do not happen. They do not probably happen. But in an idealized, abstract space, well, nothing physically happens. Nonetheless, sensible statements can be made about this world. After all, it is the abstract world of mathematics, among other things. Nothing is happening there as it is in our world. Just as an aside, yes, to listeners of Topcast, it is true that all times are equally real given general relativity. Our consciousness exists in the now, and so we see things happen. If one could take a God's eye view of physical reality, then of course, nothing happens. Existence is just there as a block universe. However, this perspective is physically impossible to take. As conscious people, we are a kind of locus of creativity, a catalyst that transforms the physical universe, making the future, in general, better than the past. We make progress, and that progress, from our perspective, is inherently unpredictable. It is of no use saying, Well, in truth, nothing happens in physical reality from a God's eye view. Now, while that's true, it is for our present purposes only because we, like the Bayesian philosophers, want to understand what to do as conscious people who want to be better prepared for an unknown future, unknown from our perspective. And there are, indeed, objectively better and worse ways to be prepared for that unknown future. One way that is worse is to assume you can know all the possible outcomes, count them up, weigh them, and then calculate the most likely. This is impossible, and is what I am critiquing here in part, because you cannot know the future. Because you cannot know the future, what follows is that you cannot possibly count up all the ways the future is going to be, much less weigh them individually and calculate the probability of each. But inside that LLM, again, we have not an infinite space of possibilities, we have a finite space of possibilities. This letter could appear next or that letter, and there are only 26 different letters, or maybe 256 different characters, say, or more if we include special symbols. Whatever the case, and however large the number, it is finite and can be known. So the next letter, or next token, or next word can be associated with a probability, because you can count up all the different possible combinations, large though they might be. At a higher level then, what emerges is a system able to reason, calculate its way to useful rearrangements of the information from its training library, which are novel, useful, and accurate. One quibble with these papers is they do anthropomorphize LLMs, which seems to be kind of standard no matter if you're on the side of the people who think they're becoming more like AGI or against that. And so, therefore, the authors of these papers do talk about the LLMs as having beliefs and confidence, that kind of thing. But we can ignore this psychologizing of LLMs. I don't think an LLM believes anything. And when you hear at least one of the authors in interviews, I don't think he thinks so either. And the LLMs don't have confidence in anything. Those are subjective mental states and therefore imply consciousness. What LLMs in fact have are assertions or statements and so on. Those statements can be more or less accurate as assessed by a person or measured against some standard. In any case, that LLMs do indeed reason, I prefer to say calculate, but whatever, that horse is bolted, in a Bayesian way, and are tending to improve in their capacity to do so, is a refutation of the claim they are able to actually create knowledge, precisely because we know Bayesian reasoning is not knowledge creation. It is at best a way of comparing already existing claims against each other. It's not a method for generating new claims. Let me say that again. These papers, if correct, show that LLMs are Bayesian reasoners, and for good reason, because they're a closed, idealized system of data on which the probability calculus can be used to make reasonable guesses about the future, predictions. And precisely because they are a demonstration or an argument for, an explanation of LLMs as Bayesian reasoners, they're therefore not creating anything. They're just calculating stuff about their own contents. Let me give a little overview of each paper. What they're doing here is checking to see whether or not probability-based reasoning, Bayesian reasoning, is actually being used by LLMs in order to do the prediction of the next words. The authors claim to have invented something called the Bayesian wind tunnel to experiment, to run tests on these LLMs. They already know the true answers to particular questions, and then they see if the LLM can actually get to that answer as well. What they show in this paper one is that the transformers seem to use something like a manifold, fancy word for kind of terrain, I suppose, and they use this manifold to construct a landscape of all the knowledge or information that is inside of its training library. The second paper, they go through how their experiments kind of work in more detail. They find out that attention is actually using this, what they call Bayesian manifold shaping of the data, and they test it. They test their model of how an LLM actually reasons, and run test after test after test. And then in paper 3, they scale up. Okay, they scale up the test because at first they use a small scale LLM, and then they use these really large LLMs to check to see if the really large LLMs also reason probabilistically in the way they demonstrate these small scale LLMs work in their earlier papers. So that's me hand waving about what I got from those papers. Again, they talk in the papers a lot about manifolds and a lot about matrices. And so it's a lot of technical stuff. It's very difficult to read through it unless you're an expert in the field. And I'm not an expert in the field, but I did my absolute best. And I listened to, as I say, interviews with the authors. My way of putting this, I suppose, spending quite a few days diving deep into this stuff, is that I now think of a large language model as something like a cartographer of human language. They're making maps. Over time, the LLM has, analyzed language, analyzed how it is that humans construct language, how they argue, explain, joke, teach, whatever. And from that, they develop this map of how conversations flow. So when you prompt, you're kind of dropping a pin onto a map. And the model's job is simply to say, from here, where the prompt or the pin has been dropped, where do human conversations usually go next? It then steps forward one word at a time, staying on paths that look like places humans have walked before. And so the authors of the paper argue it's able to do that because it uses the probability calculus and Bayes' theorem recursively. According to Vishal, one of the authors of the paper, he argues that the model the LLMs don't understand anything, which is a relief for me. Many people talk about these LLMs as understanding. He's saying they don't understand anything. All that it's doing is learning the shape, the manifold of human explanation, okay, or how the explanations are formed in language. What form extant or existing explanations tend to take. So there's a certain way in which human beings put language together and, let's say, create explanations. We create explanations with words that talk about causes, and we use examples and analogies and caveats. The model, the LLM, absorbs those patterns in our explanation construction, but the construction of explanations in language, so that when we get the explanation from the LLM, it sounds, or it seems to us when we read it, it seems like understanding. But all it's really doing is just updating probabilities. It's not thinking in the way people do. And this is me talking now, not Vishal. It's calculating. And that's something I was saying back in 2021 or 2022 myself when I was on Air Chat with Naval and explaining this day after day, week after week. I was calling the early ChatGPT models language calculators. And now we have a trio of professional papers by professionals in the field attesting to that kind of thing and sharpening up the kind of calculator that I was talking about to being a Bayesian calculator that forms maps of existing explanations and the kinds of language people use. And it can traverse the landscape or the manifold. A prompt drops a pin on the map somewhere, and there are only a finite number of places to go inside of that finite manifold. That makes sense. So I have to say, I think I've changed my mind. I think that people understand. I used to say that no one understands at a high level how to explain the sophistication and efficiency and accuracy of LLMs that has emerged from the low-level next token prediction. But now I think there is the beginnings, at least, of a good higher-level explanation. I think there exists a high-level explanation of how LLMs work, approximately. They operate according to Bayes' theorem for calculating the next letter, word, sentence, and so on. And they construct a map or terrain represented mathematically inside the program that then allows for the LLM to better predict what comes next in a sentence, in a paragraph, and so on. Let's listen to an excerpt of an interview with Vishal. And I think it's great because there's been so much confusion on this, and there's only been a few voices out there talking about what we might say is the black and white distinction between existing AI and AGI so far. And most of them seem to be in the orbit of David Deutsch. Not all, but many. And so it's good to hear this professional who works in the area also making the same noises. So let's listen to Vishal, and I'll comment.
Maybe just walk through very quickly how, like, this same model, you can just very quickly show that a model can never recursively self-improve.
So, another phrase that we've been using recently is, the output of the LLM is the inductive closure of what it has been trained on.
Yeah.
So when you say that it can recursively self-improve, it could mean one of two things. So let's get back to the...
Well, actually, what's kind of interesting is, like, often most people agree that if you have one LLM and you just feed the output into the input, like, it's not going to do anything. But then often people will say, well, what if you have two LLMs? You have no external information, but you have two LLMs talking to each other. Maybe they can improve each other, and then you can have, like, a takeoff scenario. But again, you even addressed this, even in the case of, like, n number of LLMs, using kind of the matrix model to show that, like, you just aren't gaining any information entropy.
Yeah, so you can represent the sort of information contained in these models. And let's go back to that matrix analogy that I have, the matrix abstraction. Yeah. So like I said, these models are represent a subset of the rows, right?
Yeah.
So a subset of the rows are represented, but some of these rows are able to help fill out some of the missing rows. For instance, if the model knows how to do multiplication, doing the step-by-step, then every row that is corresponding to, let's say, 769 times 125 or whatever, all those multiplications, it can fill out the answer. Because it has those algorithms sort of embedded in them, you just need to unroll them.
Yeah.
So it can sort of self-improve up to a point. But beyond a point, these models can only sort of generate what they have been trained on. So let me give you... I'll give you 3 examples.
Yeah.
So that's really important, this idea that you cannot have this recursive self-improvement from these models. This is something that many commentators have, for want of another word, been worried about. They're worried about the getaway self-improvement of maybe not LLMs, but just AI more broadly. But if the thing isn't coming up with new explanations, it cannot just continue to improve itself without limit. And yet people do still argue that these LLMs are on the way to doing that. But as Vishal is saying, as I've argued as well, they can't get outside of their training data. They can only improve on new ways to reassemble the information that is there in the training library. They're not going to go beyond it, and there is no way for them to go beyond it. Let's continue to listen.
So any model, any LLM that was trained on pre-1915 physics would never have come up with a theory of relativity. Einstein had to sort of reject the Newtonian physics and come up with this space-time continuum. He completely rewrote the rules, right? So that is an example of, AGI.
Again, I don't know if he's gotten to this independently. Most likely, I suppose, but he may have listened to Deutsch. I don't know. But this is the whole point. You can't get to, or you can't even get to Newtonian physics from non-Newtonian physics. It is a creation. It's not a derivation. And given Newtonian physics, you're not going to get to Einstein. Einstein didn't look at Newtonian physics and extrapolate. He fixed problems with it, things that were absent from it, that it could not possibly explain, that I've talked about on Talkcast many times before. And in doing so, as Vishal just said there, he rejected Newtonian, rejected what had gone before in order to literally create something new. And he says that Einstein is the AGI, right? Well, he's a GI, but basically he's conceding that AGI would be people.
Where you are generating new knowledge. It's not simply unrolling
about the universe, right?
what's
It's like it's
already
not computing
the
something.
universe.
It's actually discovering something fundamental about the universe.
Fundamental. And for that, you have to go outside your training set. Similarly,
For that, you have to go outside your training set. Yes. How? What does that mean, though? Well, as I say, it's creativity. It is the thing that we don't understand that would need the algorithm for AGI, presumably.
any LLM that was trained on it would not have come up with quantum mechanics. Right? That's where particle duality or this whole probabilistic notion or that, energy is not continuous, but it is quantized. You had to reject Newtonian physics.
Yeah.
Or Gödel's incompleteness theorem.
Yeah.
He had to go outside the axioms to say that, okay, it is incomplete. So those are examples where you're creating new science or fundamentally new results. That kind of self-improvement is not possible with these architectures.
Underscore that. This kind of self-improvement is not possible with these LLMs. These LLMs can get better, but not at that kind of thing. Not at inventing new explanations or new science or new anything, really.
They can refine these, they can fill out these rows where the answer already exists. Another example, which has received a lot of press these days is these IMO results, International Math Olympiad. Whether it's a human solving it or the LLM solving it, they are not inventing new kinds of math. They are able to connect known results in a sequence of steps to come up with the answer.
This is what I and Paul, the mathematician that I interviewed as well with Conjecture Institute, go and have a look at that, Paul Robichard, what we were talking about. They can be very, very good, these LLMs and various other kinds of AI, very good at solving high-level mathematical puzzles, like those found in maths Olympiad examinations or tests or competitions. And some people who don't know maths are very, very impressed by their ability to do this. Even if you're not a mathematician, even if you are a mathematician, I suppose you can be very impressed by that in the same way that you can sort of be impressed by a pocket calculator that can multiply two 12-digit numbers very, very quickly. Yeah. Okay, so our electronics are fascinating and amazing. Now, some people are just particularly impressed by a computer, a large language model that can do these complex math Olympiad type questions or physics Olympiad type questions, but they're not as impressed by the pocket calculator doing arithmetic. And yet it's the same kind of thing. It's working with existing axioms in order to generate a result already known, or at least already able to use processes, procedures, methodologies that have been discovered. They're not inventing new mathematics. They're just using the existing mathematics as a set of axioms and then working through the rules of inference as a computer does. It's not creativity.
So even the LLMs, what they're doing is they are exploring all sorts of solutions. In some of these solutions, they start going on this path where their next token entropy is low. So that's where I say they are in that Bayesian manifold, where you have this entropy collapse. And by doing those steps, you arrive at the answer.
By entropy collapse. He's using the word entropy as almost synonymous with uncertainty. And so entropy collapse means reducing the uncertainty down so that you've got a single response, the most likely response.
But you're not inventing new math. You're not inventing new axioms or new branches of mathematics. You're sort of using what you've been trained on to arrive at that answer. So those things LLMs can do, they'll get better at it, of connecting the known dots. But creating new dots, I think we need an architectural advance.
That's a lovely way of putting it. And I might steal that from now on. LLMs and existing AI are very good at connecting known dots. They're not any good at creating new dots, the new discovery, the thing which will solve the problem that we have in gaps of our explanations, existing explanations. So in order to go further, to get to that next new explanation that goes beyond just connecting the dots, we have to invent new dots. And LLMs cannot do that. They are forever trapped by their training data.
Yeah. So Martine was talking earlier about how the discourse, was either stochastic parrots or, AGI, recursive solving. How do you conceive of sort of the AGI discourse or even the concept? What does it mean to the extent that it's useful? How do you think about that?
So about the way I think about it, the way we have tried to formulate in our papers is it's beyond a stochastic parrot, but it's not AGI. It's doing Bayesian reasoning over what it has been trained on. Yeah. So it's a lot more sophisticated than just a stochastic parrot.
Sorry, how do you define AGI?
Okay, so AGI. So how do I define AGI? So the way I would say that LLMs currently navigate through this known Bayesian manifold. AGI will create new manifolds.
Asking for definitions is always a bad question, I think. What would I say to this? Well, just what David Deutsch says, which is AGI is a person. So by general intelligence, we mean a person. So an artificial person. Now, if you want to get into the weeds, you say artificial universal explainer. And what's a universal explainer? Well, then that opens up an entire discussion about what universality is and what explanations are and how they are created and the mystery of what it is to be a person. It's a whole conversation, which is a black and white difference, again, from normal AI, which are trapped within their training data. But no person, and therefore no AGI, would be trapped by training data. You go well beyond, you use your existing learning in order to invent, to create, to imagine brand new things that no one has ever thought of before. But the LLM is only ever using the stuff that we've already discovered to just rearrange that stuff we've already discovered into perhaps novelty, but nothing creative, nothing that's not already in there in the same way that any random shuffling of the 52 deck of cards is there in the deck of cards, if you like. The 52 cards are the normal 52 cards. What's not in there is a joker. And so what's not in there are the tarot cards. And what's not in there is everything else that isn't a typical playing card.
So right now, these models navigate, they do not create. AGI will be when we're able to create new science, new results, new math. When an AGI comes up with a theory of relativity, I mean, it's an extremely high bar, but you get what I'm saying. It has to go beyond what it has been trained on to come up with new paradigms, new science, and that's my definition of AGI.
Vishal, do you think that based on the work you've done, can you bound the amount of data, compute or compute that would be needed in order for it to evolve? So one of the problems, if you just take LLMs as they exist, is there was so much data used to create them. To create a new manifold will need a lot more data just because of the basic mechanisms, right? Otherwise, it'll just kind of get kind of consumed into the existing set of data. Like, have you found any bounds of what would be needed to actually evolve the manifold in a useful way? Or do you think we just need a new architecture?
I personally think that we need a new architecture. The more data that we have, the more compute we have, we'll get maybe smoother manifolds. So it's like a map.
Yeah, because right? I mean, there's this view that people have. They're like, well, Vishal, this is all good and well, but I could just take an LLM and I can give it eyes and I can give it ears and I can put it in the world and it'll gain information, and based on that information, it'll improve itself, and therefore it can learn new things. But
that's the era of empiricism, of course. Empiricism means you can just go out into the world, you've got these eyes, and you know what you're looking at, and you can interpret what you're looking at accurately. If you gave an LLM, it's an experiment that people could do. If you gave an LLM cameras for eyes and microphones for ears, The problem is, and even Jordan Peterson has talked about this, you have to know what to listen for. You have to know what to look at. Now, the LLM, no doubt, and AI have already been trained. You know, the Roomba vacuum cleaner can be trained to look for particular things that the coder is already aware of. But if you give eyes and ears to this LLM thing, in order that it constructs new knowledge, what does it look for? Now, if it's a person, no one has to tell it. It just becomes curious. A person is curious and looks around its environment and goes, what's that? Never seen that before. Let me investigate. Especially if you're a scientist, you know, I don't understand this thing. Let me try and come up with it. But at least I know, okay, I'm going to point the telescope at a star and look at a star. I know what a star is. The LLM won't know what it's looking for, what it's looking at. So this empiricist idea it's pure empiricism to say you can just look and then understand the world. That's not the way this works. The data that comes into the cameras has to be interpreted, given a theory. You have the theories first, then the data is collected, and in light of those theories is interpreted. And it's when you don't understand what you're looking at that then you have to create in your mind the explanation of that thing that's out there. No doubt you can program an LLM. You know, mobile phones can already do this. You can point it at stuff and it will say, okay, that's a fan, that's a can of drink, that's a tree, that's a cat. The phone could actually do that. But for things it doesn't yet know, no clue. It doesn't begin to conjecture on things that doesn't appear in its library. And that's Vishal's point here. If it's not in the library, you can give it cameras and microphones all day long, high fidelity cameras, you know, very, very sensitive microphones. And if it hears something that's not there in its data, or it sees something that's not there in its data, it will just ignore it. It won't know what to do. What are you going to do? You're going to ask it, what is that thing? It'll give you an error or something. You know, you point it at, let's say you pointed it at an insect that no one's ever seen before. Now, for a scientist, they can investigate and they can actually create explanations of what this insect is. Is it a bug or is it a fly, you know, etc. And it can develop theories. The LLM won't do such a thing because if it's not in the data, then it won't. Or any of a number of other mysteries. Better would be actually explanatory mysteries, because we can already do this kind of thing. So, for example, and I know Sabine Hossenfelder has been one who's experimented with LLMs, and anyone can do this as well, but she's posted videos about this, where you ask the LLM to invent new theories for dark matter, let's say, an existing problem that exists in astronomy, physics, science. So we can already do that. We can already give the LLM these problems that we don't yet know the answers to. And they're hopeless. They come up with laughable suggestions or just subtle variations on things they've already been programmed with. So yeah, the cameras and the microphones won't help.
The counterpoint that I've always just intuitively thought to that is the amount of data used to train these things is so large. How much can you actually evolve that manifold given an incremental? I mean, almost none at all, right? There has to be some other way to generate new manifolds that aren't evolving the existing one.
I completely agree. There has to be a new sort of architectural leap that is needed to go from the current, just throwing more data and more compute, it's going to plateau. It's the iPhone 15, 16, 17.
And are there any research directions that are promising in your mind that might help us,
Okay, so I'll stop it there because he's going to talk about what he thinks are possible ways to AGI, and he doesn't give anything that's new. He talks about, Jan LeCun, who's a famous researcher here. I would say talk to Carlos de la Guardia, obviously, because we know to some extent how knowledge is created. Then if you want AGI, you have to have an understanding of popular epistemology. Now, he doesn't mention that, so whatever. But these guys, again, even the interviewers here, you can see where their bias, for want of another word, lays. they think, like so many other researchers, that you just throw more compute, you throw more data at these things, and eventually they reach escape velocity and become AGI. And then it keeps on going to ASI. But as Vishal just said there, it's kind of like people complain about the iPhone. You know, when there wasn't iPhones and the iPhone appeared, it was a breakthrough, groundbreaking. And then for a little while, the improvements in the iPhone were very great very quickly, every new iPhone. But then as he says, the 14, 15, 16, whatever, 17, the recent iPhones are very similar one to another. I didn't bother getting the last two iPhones because I thought the one that I have, which I'm pretty sure is the 15, is good enough. And the improvements that are offered on the newer ones are just like slightly better camera, slightly longer battery life, that kind of thing. Now, the same seems to be happening with the LLMs. They're fantastic. My iPhone is fantastic. But the rate of improvement has slowed because you can only improve the amount of data, or the quality of the data, if you like, but you're not going to get much better. The responses are already as good as you would like, putting aside hallucinations and the bias that is sometimes injected into these things. But they do appear to be plateauing. Now, plateauing out at a fantastic level. I mean, what more do you want from these excellent chatbots and search engines? I think they're doing fantastic stuff. But if what your aim is AGI, they talk about new architectures. Yes, new, different philosophy, not just assuming that we can extrapolate from something that's not a person and is just a chatbot or a language calculator to something that is a creative explanation generator. Things I've talked about ad nauseum on this channel over the last few months, indeed years. Now, a lot of people are now saying this. But a lot of people have been saying what Vishal has just said, that scaling LLMs won't get us to AGI. And yeah, David Deutsch has been saying that since the beginning. And I'm not with, by the way, this new group of wet blankets who think this is a huge failing of LLMs, the fact that they won't become AGI. It's not a huge failing. LLMs are excellent. Complaining they fail because they're not able to be scaled to AGI is rather like complaining that super fast rail will never actually fly. They're categorically different things and can be appreciated for the different things they do. By the way, it's interesting too, neither Grok nor ChatGPT nor Claude seem to know how they themselves work when I ask them. You ask them, explain how LLMs work at a high level. And by high level, again, I mean emergent, not reductive. The interesting thing is when I interrogate ChatGPT about how is it able to achieve what it achieves, at least it says it has no beliefs, and no LLMs have a belief. Okay, that's enough for today. I promise that next time I will go back to regular programming unless some sort of world war breaks out or something like that. We will go back to the fabric of reality. But until then, goodbye.